Hey, welcome back to Math with Patrick. Today is February 10th, and we have problem number 41 from this Daily Epsilon calendar. All right, how many minutes after 2 p.m. do the hour and minute hands meet? Okay, well, this is like I'm actually kind of surprised that we have a clock problem today. It's very mathy. We're counting, there's numbers, there's geometry involved. It seems a little simple, but here, let me see if I can just try figuring it out. All right. So usually 12 o'clock's up here. There's 3, 6, 9. And then after I label those numbers, now I can go in and evenly space out the other hours. That does not look like a 4, so let me fix that one. 7, 8, 9, 10, 11, and then back to 12. All right. So let's see, 2 p.m. So on the clock, 2 p.m. looks like the hour hand, which is the shorter one, going right towards the 2. Let me try fixing that. The hour hand goes right towards the 2. And then the minute hand, which is longer, will go straight up to the 12. Every 5 minutes, it'll tick over this way. And every hour, the minute hand counts out 60 minutes, or an hour. And then the hour hand will tick over one spot. So by the time it hits 3 o'clock, the clock will look more like this, and this hour or this minute hand will have gone a full revolution. So at some point after 2 o'clock, that's 3 o'clock again. Why am I drawing these things? There are these amazing online resources that you could find here. Let me hop on over to an interactive online clock. All right, so here I am on Toy Theater. It's like a nice website for like games and math puzzles for students. You can explore it yourself. Toy Theater. Anyways, so here, let's see, can I click and drag? Ooh, nice. So I can click and drag on the hour hand, or I can click and drag on the minute hand. There we go. So I want to do 2 o'clock, and I don't know, it just feels better to do 2 p.m. instead of 2 a.m. So it's 2 p.m. right now. The hour hand's pointing towards the 2. The minute hand is pointing towards the 0. And so 2:05 looks like this. The hour hand will have moved a little bit more. 5 more minutes can elapse. Now we're pointing at that 10 for 10 minutes. And the hands almost overlap. Let's see what happens if I tick it over to the next minute. Oops, that was the wrong one. Okay, so when they're at the 11 or 2:11 or 11 minutes, however you want to think about it, they look very overlapped with each other, which is strange because today's date is the 10th, so I'm not exactly sure how I'll be rounding. So here's where the math comes in. We'd have to figure out how many degrees each of these hands moves every minute or maybe even every second. And I want to get down to maybe the fraction of a second. When is it actually? When is it between 2:10 and 2:11 that the hour hand and the minute hand perfectly overlap? I'd like to compare the rates of the hour hand and the minute hand, and I think a convenient unit for these rates should be degrees per second. That way I can compare their rotations with each other. So a whole circle is 360 degrees, and let's see, I guess I should really only look in this quadrant right here because that's when they're going to overlap. If I split it up like this, I'll get 30 degrees in each of these sections. One way to think about it is I'm just splitting 90 degrees into 3 chunks. Or you could think about the whole 360 degrees all the way around the clock. There's 12 hours, and that 36 divided by 12 is 3. So 360 divided by 12 should be 30. All right. So let's see. Actually, maybe not degrees per second, but maybe like degrees per minute might make a bit more sense because I don't know really how to measure seconds on the clock just yet. Maybe later I can divide by 60 and get seconds. So let's do the minute hand first. So for the minute hand, let's find maybe the speed of the minute hand in degrees per minute. Well, each minute that passes, I will go some amount, maybe 5 minutes is going to be the same as 30 degrees. Oh, but I wanted degrees per minute. That made a bit more sense to me to do per minute. Usually speeds or rates have time on the bottom. So the minute hand goes 30 degrees every 5 minutes. Okay. And then the speed of the hour hand, let's see. Well, the hour hand is going to go from the 2 to the 3 in an hour. So it's going to go 30 degrees in 60 minutes. Okay. I guess I could simplify this a little bit because these are just fractions. And if I wanted to find a unit rate, I could do the 30 divided by 5 to get a 6 degrees per minute for the minute hand. And then I could do 30 divided by 60 and I get half a degree per minute. So each minute that elapses, now I know the exact amount of degrees each of these hands is going to move. And it looks like the hour hand has a head start. So in addition to finding their rates, I should also know their positions. Let's just say maybe X for position. So currently the X position of this minute hand, I'm just going to define that up direction as 0. I think it'd be convenient to think of 0 here and then increasing as I go in the clockwise direction. So the position of my minute hand will be 0 degrees and then plus its rate, which was 6 degrees per minute, and then times time. And I think I'll do time in minutes, and I'll just keep it as a t. The position of the hour hand, and that one has that head start, so it's going to be already at 60 degrees here, but then it moves at a slower rate, so it's only going to be half a degree per minute, so that's its rate or its speed. And then I'm going to do speed times time to figure out the resulting position after a certain amount of time. And then the units are kind of clouding my math abilities here, so I'm going to simplify a bit. That 0 doesn't do anything, so I have a 6t for this position, and then I have a 60 plus half t for this position. And eventually their positions are going to be the same, so I could set these two equal to each other. So I could set 6t equal to 60 plus half t, and setting them equal to each other means that their positions are going to be equal. And it's going to be really nice to be able to solve for t so that I can find the time where they overlap. Because that's the whole point of this problem, is figuring out the time when the positions of the hands are the same. So solving this algebra problem, I could subtract a half t from both of these. So I do get 5.5 here. I think it might be nice to think about it as an improper fraction. So this is the same as 5.5 because I have 10 halves and one more, and this is just 5. Okay, so I have 11.5t is equal to 60. Okay, and I want to undo this part. And my favorite way to undo a fraction is just to multiply by its reciprocal. So I'll multiply both sides by the reciprocal. These all cancel out, and I'm able to solve for t. T is equal to, I'll multiply the top part first, 120 over 11. Okay, what does this number mean? I think earlier I said that this t was in minutes, so I'm pretty confident in that. And I think this tells me how many minutes after 2 o'clock the hands overlap. Let's try it out with long division, actually. So how many times does 11 go into 120? Well, clearly it goes in 10 times at least. Then that multiply step, subtract step, I bring down a 10. Okay. And 11 doesn't go into 10 evenly. So I think here it might be nice to do the strategy where I have more of these zeros to bring down. So 11 doesn't go into 10 evenly, so it goes in no times. But I could bring down this other 0, and now imagine how many times does 11 go into 100? And this time it can. Well, it goes into 99 9 times. Do that multiplication here. I'll subtract, and I get a 0.1. Okay. Then after the subtract step, I'll bring down. I'll ask myself, how many times does 11 go into 10? It doesn't. And so I need to bring down the next 0. And I'm kind of getting this cyclical pattern. How many times does 11 go into 100? 9 times. I'll do the multiplication just to show it. I get a 1. I could keep doing these zeros infinitely because 120.00000, like it's still the same as 120. And so all of these zeros are really convenient to help me find a decimal approximation to my fraction division. Let's see, I'll bring down this 0, 11 doesn't fit, so I have to bring down the next 0, and then it's going to be another 9 times. So I could just say it repeats here, and just, I don't need to show all those numbers. That bar says that it'll go 909090 forever. So this is the exact minute, 10 minutes, 0.909090 minutes that these hands overlap. And I guess if I'm rounding down, it is 10 minutes. So that's today's date. But like, if I'm rounding to the nearest minute, I'd pick 11. Oh, you know what? Maybe it means at 2 hours, 10 minutes, and some amount of seconds. That's when the hour and minute hands meet. And so we would see a 10 minutes on the clock, and that is when they overlap. And mere seconds afterwards, it would tick over to an 11. Okay, so I guess I'm okay with the answer being 10 because it would be 2 hours, 10 minutes, and some amount of seconds. So that's the answer. We can be all done for today. I mean, stick around if you're curious. I think we can figure out how many seconds it'll be too. So that's what I'll try to solve. Let's see. So going back to my decimal, let me actually put all those extra 9s and 0s there. Just a few more. And then maybe I'll round this one to a 1. I don't know. I probably didn't have to go that far. So this is some amount of minutes, and then I have a fraction of a minute here, and I want to convert that to seconds. And I know that there's 60 seconds in a minute. So if I do 60 times 0.9090 repeating, I will get an amount of time in seconds, and that will be what will show up on the clock. So to do this multiplication, actually, you know what? It might be easier to convert this back to a fraction. This one is going to be, I think that's 11 twelfths. And no, wait, sorry. What is that? 10 elevenths? Yeah, that makes sense. Because if I do this division over here, I can see that I have 110 elevenths and 10 more elevenths. This is the part that created my 10 minutes, and this is the part that I have left over. So if I do 60 times 10 elevenths, again, this is the fraction of a minute that I had on the clock that I want to convert to seconds. That's going to be 600 over 11. And now I kind of have to just run through that long division again until I find some kind of repeating decimal. So I'm already setting up all of those repeating zeros at the end to help me find a good decimal approximation. Let's see, 11 goes into 65 times. So I'll subtract out the 55, bring down the 0. 11 goes into 54 times because that's a 44. Do the subtract step, I get a 6, bring that down. Oh, cool. And I think, yeah, this repeats. So then 11 goes into 60 5 times. I'll get a 55, subtract, I'll get a 5, bring down the 0, and then looks like this is my pattern. It'll just keep repeating back 5 4 5 4 5 4. And at this point, I'm kind of happy to round, and I'll say it's going to be 54 seconds and half a second, because 0.545454, that's really close to 0.5. And at that point, you might time a stopwatch, and you really are only going to go to some fraction of a second. I don't think I need to be more precise than half. So at 2 o'clock, or 2 hours, 10 minutes, and 54 and a half seconds, that is when we can expect the hour hand and the minute hand to precisely overlap. And if you want more precision, you can just tack on more decimal points. And our minutes do say 10. That's today's date. So there's your answer. Hope you enjoyed. I'll see you next time. Bye.